Hello guys, so in this video I'm going to talk about the concept of how to compute a surface integral, and we're asked to compute a surface integral bounded within the region of below the plane z is equal to 1 plus x plus y and above the rectangle of 0, 5 times 0, 2. So one thing I will point out is I want you to pay attention to this formula right here. So f of x, y, z times ds is equal to the surface integral of that f of x, comma y, comma g of x, y, and then the square root of partial x squared plus partial y squared plus 1 times dA. So without further ado, for step 1, we're going to identify f of x, y, z. So we know that f of x, y, z, at least according to the formula, which is true, is equal to f of x, comma y, comma g of x, y. So we know f of x, y, z given to us is 6zxy, or I'll rewrite it as 6 times x times y times z. And we know f of x, comma y, comma g of xy is equal to 6 times g, and then we're going to substitute the z that we're given in the region for g of xy. So we can get in terms of xy, so it's 1 plus x plus y. So all I did right here was substitute z for the region below the plane of 1 plus x plus y. So f of x, comma y, comma g of xy is equal to 6xy, and we're plot times 1, and we're distributing the 6xy to each term, plus 6xy times x plus 6xy times y. So now what we're going to do is we're going to simplify this a step further, and we know this is equal to 6xy plus 6x squared y plus 6xy squared. So that's our f of x, y, z. So basically what we're going to do is we're going to identify all the variables, and then we're just going to plug it into the surface integral formula. So that's the easiest way to do it. So let's move on to step 2. So now that we did step 1 and step 2, we're going to go ahead and find the partial derivatives, partial x and partial y. So we're going to do this from the z, the region z that we were given, the plane, which was z is equal to 1 plus x plus y. So in doing so, the partial with respect to x, partial of z with respect to x is simply 1. The partial z with respect to y is 1. If you don't know how to take partial derivatives, you should by now, but if you don't, I do have a video on that. And for step 3, we're going to identify the limits. Well, we were given a rectangle. It was above the rectangle 0, 5, 0, 2. And since we weren't explicitly told which one is x and which one is y, we can safely make the assumption that the first one is x and that the second one will be y. Thus, our x limits are 0 to 5, and our y limits are 0 to 2. So now for step 4, now that we have the limits, the partial derivatives, and we know our f of x, y, comma g of x, y, z, we're going to set up the surface integral. And this is basically like a double integral. It doesn't matter whether x or y goes first, but I'm choosing x, and we know f of x, y, g of x, y, and then we know for the radical we need partial z with respect to x squared plus partial z with respect to y squared plus 1 times dy dx. So now we're going to plug in everything we have. So we know that the limits of x are from 0 to 5, the limits of y are from 0 to 2, and we're plugging them in accordingly. What was f of x, y, g of x, y? Well, we did this already. 6xy plus 6x squared y plus 6xy squared. And then inside the radical, partial z with respect to x was 1 squared, plus partial z with respect to y was 1 squared, plus 1, then dy and dx. So now that we have our surface integral set up, all we simply do now is just treat this as a double integral, and we're going to go ahead and move forward with this and integrate it. So since we're integrating with respect to y. I'm going to have the x limits. I'm going to pull them out. I'm pulling out the constants. The square root of 1 squared plus 1 squared plus 1 inside of square root is 3, so I factor that out. I factored out the 6, and we're left with xy plus x squared times y plus x times y squared times dy. Then dx I'm right over here, so that way we're focused on just the y. So when we integrate this with respect to y, and we plug in the limits and solve, when we integrate this, we get x, and then we integrate y, so it's y squared over 2 plus the constant x squared, and then we integrate the y again, it's y squared over 2, and then plus x, and then we integrate the constant, we integrate y squared, so we get y cubed over 3. And this is bounded between 0 and 2. So now what we're going to do is I'm going to try to get the least common denominator just because it'll make it a whole lot easier on me. So before I plug in, I'm going to try to get a least common denominator. So x over 2, x squared over 2, x over 3. All I did was simply just isolate the y terms because at the end of the day, that's what we're going to, so that way we know what we're plugging into. And now what I'm going to do is I'm going to multiply by 3 over 3 times x over 2 times y squared. And all I'm simply doing is I'm trying to get a common denominator because it just makes it way easier when you plug in. So I multiplied by 3 over 3 plus 3 over 3 times x squared over 2 times y squared plus 2 over 2 because I want a common denominator, so 3 times 2 will give me a common denominator of 6, x over 3 y cubed, and then from 0 to 2. So notice now we have the square root of 3, and then we have 6 divided by 3x y squared over 6 plus 3x squared y squared over 6 plus 2x y cubed over 6 bounded between 0 and 2. So now we have a common denominator of 6. So let's go ahead and factor out the 1 over 6. So inside the brackets we're left with 3x y squared plus 3x squared y squared plus 2x y cubed bounded between 2 and 0. And we can cancel out the 6's, and we're left with the square root of 3 times 3xy squared plus 3x squared times y squared plus 2xy cubed. So now let's finish plugging in. So let's continue plugging in. So the square root of 3 times 3x squared 2 squared, and we're plugging in everywhere we see y, we're going to plug in the bounds. So 3x squared, and now you see y I factored out of 1 over 6, so that way having a common denominator makes it easier to plug in. So 2x times 2 cubed minus, and now we're plugging in the second boundary, which was 0, so 3x parentheses 0 squared plus 3x squared 0 squared plus 2x 0 cubed. And now these go to 0, all three of these terms go to 0. So in essence, all we have to do now is just compute the 2. So the square root of 3 is equal to 2 squared is 4, 4 times 3 is 12, 12x, plus 2 squared is 4, 4 times 3 is 12x squared, plus 2 cubed is 8 times 2 is 16, so 16x. And now what I'm going to do is I'm going to factor out a 4 out of each term, and I'm left with 3x plus 3x squared plus 4x. So now I can integrate this function with respect to x. So now we're going to integrate this with respect to x. So what we're left with is 4 that we factor out the square root of 3. We're left with 3x plus 3x squared plus 4x times dx. So bounded from 0 to 5. So now we're going to integrate this with respect to x, and we're left with 3x squared over 2 plus 3, and then x squared integrated is x cubed over 3 plus 4, and then x integrated is x squared over 2. And this is bounded between 0 and 5. And notice how we can cancel out the 3's and we can simplify 4 over 2, we can simplify it to 2. So now furthermore, 3 over 2x squared plus x cubed plus 2x squared, because 4 over 2 is 2, bounded between 5 and 0. And now what we're going to do is we're going to plug in 3 over 2 x squared plus x cubed. We're going to have a common denominator of 2 for each term, so that way we can factor out something, because it makes it easier when we plug it in. So 2 over 2 times x cubed plus 2 over 2 times 2x squared, bounded from 5 to 0. And notice how we can cancel out the 2 on each denominator. We can factor it out and we can simplify 4 over 2. Thus we're left with 2 radical 3. And inside the brackets we're left with 3x squared plus 2x cubed plus 4x cubed, 4x squared, bounded from 5 to 0, from 0 to 5. So now what I'm going to do is I'm going to combine the like terms. So I know 3x squared plus 4x squared is equal to 7x squared plus 2x cubed, bounded from 5 to 0. So now, since I made sure I had a common denominator and I factored it out, now the plugging in part is very easy. So I know 2 radical 3, 7, 5 squared plus 2, 5 cubed, minus 7, then we plug in 0 squared plus 2, and we plug in 0 cubed. And then we know these terms go to 0, and we're left with 2 the square root of the radical 3. We know 5 squared is 25, times 7 is 175. And you can use your calculator at this point. You don't have to do it in your head. And we know 5 cubed is 125, times 2 is 250. And minus 0, so we know that 0 is out. So we're left with radical 2, 3, times 250 plus 175 is 425. And 425 times 2 is 850, radical 3. And that's the answer to this surface integral. So basically, in quick retrospect, all we did was just compute the variables of the surface integral. We took the f of xy, comma g of xy. We took the partial x, partial y. We found the limits, we set up the integral, and we basically computed a double integral. So that's it to surface integrals. Nothing more to it. Just basically just follow the steps and it becomes really straightforward. So let's move on to a different example. So in this example, we're asked to find the mass using the surface integral, given the plane 25 minus z is equal to 25 minus 3x, 3.5x minus 2.5y, above the rectangle of 0, 2 times 0, 1, and we're given the density of 100 minus 4z. So we're not explicitly given a function of x, y, z like in the previous problem. So what do? Well, the first thing we need to do is identify our f of x, y, z. And whenever we're trying to find mass, a surface integral can be used whenever we're given a function of density. So the integral of a function of density with respect to f of x, y, z can give us mass. So that's how we're going to use a surface integral to find mass. So then what would our f of x, y, z be? Well, our f of x, y, z is going to be our density. So our density is f of x, y, z. Furthermore, our f of x, y, z is equal to the function of density given, which is 100 minus 4z. So now, what we're going to do is, we want this in terms of the surface integral, so we want this in terms of f of x of g of xy instead of the z. So how do we do that? Well, we have 100 minus 4, and then for z, we can just substitute the region below the plane. So z would be 25 minus 3.5x minus 2.5y. So then from there, all we literally do is just distribute the 4 out. So f of x of g of xy is equal to 100 minus 4 times 25 is 100. 4 times negative 3.5 is minus 14x. And then 4 times 2.5 is minus 10y. Furthermore, now we're going to distribute the minus sign to each term separately. So 100 minus 100 minus negative 14 would be positive 14x, minus negative 10y would be plus 10y. And notice how the hundreds can cancel each other out. So our f of x of g of x y is equal to positive 14x plus 10y. So now that we know our function, the next step is going to be to find the partial derivatives with respect to z of the plane z. So we know the plane z in this case was 25 minus 3.5x minus 2.5y. So we know that the partial with respect to x is going to be minus 3.5. Partial with respect to y is going to be minus 2.5. So for step 3, we're going to identify the limits. So we are given x is from 0 to 2. So x naught is 0 and x of 1 is 2. And then for y, it's bounded from 0 to 1. And how do I know this? Because we're given the rectangle, as in the previous example. It didn't explicitly tell us what was x and what was y, so we assume the first one is x and the second one is y. There's no need to assume otherwise unless otherwise stated. So our x naught is 0, y naught 0, our x of 1 is 2, our upper y bound is 1. So now, without further ado, we're going to set up the integral, the surface integral for step 4. So we know mass, again, is equal to y naught to y1, x naught to x1 of the function f of x, y, z, which was our density function that we already got in terms of f of x, y, z, comma g of x, y, z. And then inside the radicals, partial x squared plus partial y squared plus 1 to the dx times dy. Remember, when we have dx, we integrate with respect to x, and we have dy, we integrate with respect to y. So now let's set up the integral. So we have all the variables. Now let's set them up. So we know our m is from 0 to 1, y bounds, and the x bounds are from 0 to 2. Our f of x, y, z, we computed it to be plus 14x plus 10y. And then inside the radical, it's negative 3.5 squared plus negative 2.5 squared plus 1 dx dy. So now let's integrate. this function. So we can factor out a 2 from 14x plus 10y. The y bounds are from 0 to 1, the x bounds are from 0 to 2, and what we're left with is 7x plus 5y because we factored the 2 out. And inside the radical, we know that partial x squared, which was negative 3.5 squared, gives us 49 over 4. You can plug it in your calculator, or you can get a numeric value. I always see it easier to have it in fraction form because then you have a common denominator and you can factor that out. So 49 over 4, and then we know 2.5 squared is 25 over 4 plus 1, and we can turn this one into a 4 over 4. So now times dx and dy. So with respect to x, the first thing we're going to do is we're going to simplify that radical. So 7x plus 5y, and then we know 49 plus 25 plus 4 is equal to 78 divided by 4 and dx and dy. So now we can simplify this because we know 2 in the numerator, and then the square root of 4 is 2 times the square root of 78. So why is that a 2, not a square root of 4? Square root of the 4, that's why. Then from 0 to 1, and then the x bounds are from 0 to 2, 7x plus 5y, dx, dy. So now we can integrate this with respect to x. So let's go ahead and plug in the limits and solve. So we know the 2's canceled each other out. So that's why I always like to have common denominators, because it makes it easier. It always does. So we know when we integrate this with respect to x, we get 7x squared over 2 plus the 5y is a constant, so 5y times x. And putting parentheses around your x terms will help you in terms of computing. So that way you don't mess up, you integrate with respect to y on accident. So that's why I like to use parentheses. And this is bounded from 0 to 2. Furthermore, the square root of 78, 7 over 2, 2 squared plus 5y, 2 minus 7 over 2, 0 squared, plus 5y of 0. So all I'm doing now is just plugging in the bounds, the x limits, and in doing so, I know these terms go to 0 because they zero out, and we're left with just the first part of the problem. So the square root of 78, and we have 7 over 2 times 2 squared is 4, 7 times 4 is 28, divided by 2 is 14, plus 5 times 2 is 10, so we get 10y, minus the 2 terms zero out, so that term goes to 0. So now let's integrate with respect to y. So we know the square root of 78, 1 over 0, 14 plus 10y dy, and we already set it up. So first thing we're going to do is we're going to factor out a 2 because 14 plus 10 are both even numbers. So 2, the square root of 78, bounded from 0 to 1, we're left with 7 plus 5y times dy. And now we're literally just going to integrate this with respect to y. So the integral of 7 with respect to y is 7y, and the integral of 5 with respect to y is 5y squared over 2, bounded from 0 to 1. And now what we're going to do is we're going to have a common denominator, so that way it makes it easier when we plug it in. So we know 2 over 2 times 7 times y is equal to 5 over 2 times y squared, bounded from 0 to 1. And from there, we have a common denominator of 2, so we know 2 over 2. We can factor out the denominator of, which is 2. So we're left with 14y, because 2 times 7 times y is 14y. And notice how you leave the 2. Notice how I didn't cancel out these 2's right here. I didn't cancel these out. Why? Because I wanted to factor this one and this one. So that's why I'm left with 14y plus 5y squared from 0 to 1. So now from here, I can cancel these 2 out. These 2's out. It makes the problem a lot easier. Now I'm left with 78, 14, 1 plus 5, 1 squared minus 14, 0 plus 5, 0 squared. And I know these terms can zero each other out, and I'm left with just the first terms. So I know the square root of 78 is equal to 14 times 1 plus 5 times 1 squared is equal to 19 minus 0 squared, and I know that goes to 0. So I know my surface integral, my mass, which is what I was trying to compute, is equal to 19 times the square root of 78. So that's it for this video. So basically a surface integral is an extension of a line integral, and we can use surface integrals to compute mass given density. So, and the key is to just try to turn this into a double integral by identifying all the variables and following the steps that I listed to get to the proper answer. Thank you for watching. I hope this was helpful.